Okay, this is interesting. For each law of exponents that we have, that we've already studied, like when I'm multiplying like bases, I add the exponents, there's a corresponding law for logarithms. And so that's what we're going to look at next, are the laws of logarithms. Now we're going to be writing these in base B, kind of the generic log, and we're also going to be writing these in natural log, because again, it's natural log that we're going to be seeing a bit more often. Our first law of logarithms is log base b of b is 1. Now if we take and rewrite this, remember b is our base, so I'd have b to the first equals b. Okay, now in terms of natural logs, this means that the natural log of e is 1. This is a simplification that's going to come up very, very often, so it will be very important to remember that the natural log of e is 1. Our next law of logarithms is log base b of 1 is 0. Again, my base here is b, so I have b to the 0. Anything to the 0 power is 1. Of course, unless we're working with limits, but we're not. So b to the 0 is 1. That comes from right here. Now in terms of natural log, this means the natural log of 1 is 0. This shows up a lot, and this is a nice simplification, so we want to remember as well that the natural log of 1 is 0. Okay, this next one is actually a bit of a trick. Log base b of 0 is equal to some value of t, and what we're trying to do is we're trying to establish, is this a true statement? Well, remember how we will rewrite it. B is my base, b to the t is some value, equals 0. Is this even possible? If I have a constant here, b, is there anything that I can raise b to get me 0 back? And you might say, well, let b equal 0. But remember my restrictions. B had to be greater than 0 but not equal to 1. So this is not even possible. Log base b of 0 is undefined. It's not possible. Well, how this relates then to natural log is the natural log of 0 does not exist. I'm going to scroll up here and look at this graph again real quick. The natural log of 0 does not exist. So if we look at this graph, the natural log of 0 would be this origin point right here. I'd have to plug in 0 to see what I got back out on this natural log graph. This blue graph is the natural log graph. And if you look at that graph, I don't ever touch the the y-axis, so there's no way that that can be defined. So again, that's a kind of a trick. The natural log of 0 doesn't exist. A lot of times people like to say, oh, the natural log of 0 is e, or the natural log of 0 is 1, because of these relationships up here. But the natural log of 0 is actually undefined. It does not exist. Okay, this next one is a pretty common one, so if you've ever studied logs before at all, you probably remember that the log of a product is the sum of the logs. Now this works with log base b, and this also works with natural log. So for here, when I have a log of a product, and this has to be multiplied together, I'd get log base b of x plus log base b of y. The way this translates to natural log is the natural log of the product xy is ln of x plus ln of y. And the way I remember that is just by the saying, the log of a product is the sum of the logs. Okay, our next one involves quotients. The log base b of a quotient, x divided by y, is equal to the difference of the logs. So the log of a quotient is not the quotient here, this should be the difference of the logs. So let's go ahead and fill in difference here. So again, this works with ln as well. The ln of x divided by y is equal to the ln of x minus the ln of y. And again, this rule follows directly from the fact that if we flip y up top, I have x, y to the negative 1. Well, that's a product. So I could rewrite this in terms of a product. And then of course I'd look at the difference here. The log of a product then would be the sum of the logs, and then I have a negative exponent that I can work with using one of my next rules. Okay, this next one we're going to look at a couple different ways. This is looking at the log base b of 1 over x. Well, first of all, remember that this is a quotient. So if I wanted to, I could rewrite it as log base b of 1, because remember the log of a quotient is the difference of the logs. log base b of 1 minus log base b of x. But of course, we already know that log base b of 1 is 0. 0 minus log base b of x is just negative log base b of x. So I can solve that way as well. It works the same with ln. Works identically to the same as ln. And remember, the ln of 1 is 0. But I could also rewrite this a little bit differently using my next rule. And we don't know this rule yet, but we're kind of use this to introduce the concept. I could take 1 over x and rewrite it as x to the negative 1. My next rules, or my next law of logarithms, says if I have the natural log, or log base b, okay, of an argument to a power, I can pull the power out front. And so that's what we have here. If I rewrite this as x to the negative 1, I can pull the negative out front and rewrite. Okay, so let's go ahead and have a look at that rule. Okay, so this is the rule we were talking about. This says that if I have log base b of my argument to a power, I can pull the power out front. This works with log base b of x, and it works also with your ln of x. This is a key concept that we will use a lot. In fact, we're going to be using it in a technique called logarithmic differentiation a little bit later in this particular section. Let's go ahead and look at some examples using these laws of logarithms. Okay, the first example that we're going to look at, we're looking at combining log base 25 of 30 plus log base 25 of 5/6. So we want to use these laws of exponents and our laws of logarithms to combine these. First of all, I note that my bases are the same, and because my bases are the same, I can work backward. I have a log of the sum, and I can change this into the log of the product then. The rule that I'm going to be using here, I'll try and scroll up slowly. Here it is, this one right here. The log of a product is the sum of the logs. So we're working backward. We're saying the sum of the logs is the log of the product. So when we rewrite this, this is going to be equal to log base 25, and this only works if both of these bases are the same, of 30 times 5/6. But of course 5/6 cancels in with 30. 6 goes into 35 times, so I'm left with log base 25 of 5 times 5 is 25. So this is kind of asking a question. 25 to what power would be 25? And of course we know that that power is 1. So this entire expression up here equals 1. Let's go ahead and look at another one. This time let's be working with natural logs. Now when we're working with natural logs, remember all the rules are the same. I do have that log base e, but I just abbreviate with ln. Well, I see a couple different ways we could work this problem. First of all, I could rewrite as root e as e to the 1/2. And remember, when you're raising a power, or sorry, when you're multiplying like bases, you add your exponents. So I could combine the 1/2 and the 7/5. Another thing that I could do is I could look at this and say, okay, this is the log of a product. The log of a product is the sum of the logs. And that's the rule I'm going to use. And again, I could use the other way as well. So this would be the ln of e to the 1/2 plus the ln of e to the 7/5. Then each of these simplifies by pulling this exponent out front, 1/2 ln of e plus 7/5 ln of e. And of course, the ln of e is 1, and I'm left with 1/2 plus 7/5, which is equal to, common denominator would be 10, 5/10 plus 14/10 is going to be equal to 19 over 10, and that's my solution. And again, I could have done this differently. I could have multiplied like bases, added the exponents, pulled that exponent out front, and it would have gotten to the same solution, just a little bit different way. Okay, for this next one we're going to use the natural log in order to solve for x. So we're not simplifying, but we're actually going to solve for x in this one. First of all, we'd like to isolate x as much as we can, and we really can't do too much here with this one. I get e to the negative 4x is equal to 2/6. e to the negative 4x then would equal 1/3, of course. Now the problem here is my x is not in the base, it's in the exponent. So how do I get it out of the exponent? Well, you take the natural log of both sides, and that's the key here. So I have the natural log of e to the negative 4x, and of course whatever you do to one side you have to do to the other, is equal to the natural log of 1/3. Now over here on the left I can pull this negative 4x out front, and I'm left with negative 4x natural log of e equals natural log of 1/3. And of course this is showing up again, the natural log of e is 1. So I'm left with negative 4x equals the natural log of 1/3. Solving a little further, I have x equals the natural log of 1/3 divided by negative 4. But we can go even further with this. Natural log of 1/3, that's the same as the natural log of 3 to the negative 1. And of course from here I can pull that negative out front, and I get x is equal to the natural log of 3 over 4. That's my solution. Now is there a way to check it? Yep. I could take this value of x, plug it right into my exponent, simplify and work, use my definitions of logs, and I should get 2 back out. And I do if you do check.